Welcome to the lecture on lamellar cracks and stress corrosion cracking. So, we are going to talk about these two different type of cracks which take place. Lamellar cracks are also known as lamellar tearing, and stress corrosion cracking is certainly a type of cracking where you have the chance of cracking because of the subjection to corrosive environment or other factors. So, we will talk about these two cracks. So, lamellar crack or lamellar tearing, that is occurring in the HAZ due to combination of localized stress and low ductility of metal in through thickness direction. So, basically in that through thickness direction you have these tearings are observed, and it is because of the combination of the localized stress as well as the low ductility of the metal. So, what is happening that this is due to the presence of the elongated stringers of the non-metallic inclusions. So, parallel to the rolling direction. So, when the metal is subjected to rolling, so you will have the elongated stringers, and so they are basically the stringers of the non-metallic inclusions. Normally you have the MNS, that is manganese sulphide, or you may have the oxide silicate type of inclusions are there. So, it is because of the presence of these materials you will have the decohesion. That is what we will see, that the crack initiation basically occurs because of the decohesion of these non-metallic inclusions near the weld in or just outside the HAZ. So, basically when you have these non-metallic inclusions, so there will be decohesion that will be occurring so with the weld metal of these inclusions, and that basically will lead to the formation of these lamellar tears. So, this these in the case of lamellar tearing, these crack are appearing closely associated with the edge of the HAZ. So, you will be looking at it normally you will be seeing it as the as close to the edge of the HAZ. Now, if you talk about the lamellar tears, and if you try to visualize, so this is how the lamellar tear is looking like. So, so if you talk about the susceptibility of the lamellar tearing, now lamellar tearing is so its susceptibility, if the material is whether it will be susceptible to the lamellar tearing, that will be depending upon the one is the type of joint, second is the inherent restraint if that is there. Then you have the sulfur and oxygen content of weldment in the heat affected zone, then type and morphology of inclusions in the base metal. You have the hydrogen content of the weld, and the use of thick plates. So, apart from that you have also the preheating. So, preheating is another factor, and also the strength of the material of the electrode which is used, that also is among the factors which are making it either more or less susceptible to the lamellar tearing. So, if you look at the effect of hydrogen basically, so it will be related to the presence of or the occurrence of embrittlement rather than the cold cracking. So, there you have the chances of you have the probability of having the hydrogen embrittlement in those cases. Now, if you talk about the preheating, so preheating will be reducing the chances of lamellar tearing as the point indicates. So, especially when your S2 potentials are present in those cases these chances of or susceptibility to lamellar tearing is basically reduced in the case of preheating. So, if you have also if you are talking about the strength of the material of the electrode. So, if you take the electrode material of smaller strength and within the design requirements of course, then in those cases the weld metal will have the ability to accommodate these strains which take place, because there will be contraction strains that will be caused while cooling, and in those cases you will have the the less chance of or less susceptibility towards the the formation of these lamellar tears, and so you will have the more resistance to the lamellar tearing. Now, if you talk about the factors which are basically responsible for the initiation of the lamellar tearing, then lamellar tearing initiation basically is promoted by many factors, and among them you will have one is the interfacial separation between inclusion and the metal. So, you will have basically the separation will be there in between the inclusion, which we have seen that you have the sulfide or the silicate inclusion, oxide inclusions are there. So, these so that separation which will be taking place between these inclusions and the metal. So, that is one of the reasons. Another is the shattering of inclusions itself. Many a times the inclusions shatter, and then you will have at more locations you have the inclusion particles, and also if they shatter, then the cohesion which is there between the metal and the inclusion, although it is less, but then by shattering process that further reduces. So, that also increases the probability of having the initiation of the lamellar tearing. Then the presence of submicroscopic inclusions. So, if you have the submicroscopic inclusions and in the presence of inclusions itself, that may increase the probability of the initiation of the lamellar tearing. Then as we have discussed that you have the silicate and sulfide inclusions are there typically. So, if these inclusions are there, then they will be increasing the chances of initiation of the lamellar tearing of the material. So, that is what normally we see in the case of the lamellar tearing. Now, if you look at the other reasons, then lamellar tearing may also be due to the bending in the direction of rolling. So, bending is as we know, this is the segregation of carbon. So, in bands, so in many zones you see these carbon, and in those cases you have the appearance of the cracks. So, that can be seen in the case of lamellar tearing. We have seen the picture. So, that is what you see these bands. These are the bands which is seen, that is segregation of these carbon which is seen in the case of in bands. So, this is the example of typically the formation of the lamellar tearing. So, what you do, you have you normally do certain measures, you take certain measures to basically you have to have certain remedies for the for these occurrence of these lamellar tearing. Now, for that what you do is you use these you are using the steel with low sulfur content. So, as you know that if the sulfur will be less, then you will have the less chances of having the sulfide inclusions. So, you try to have the lower value of sulfur lesser than 0.007% even in that case. So, in those cases you can get rid of the these lamellar tears. Then you have other way by which you can get rid of these type of tears is that you treat these steels with rare earth metals like cerium or so. So, in those cases the chances of having these lamellar tears is reduced. Then you have also to use those processes, or you have to adopt those methods by which you can ensure that there will be less amount of hydrogen, that will be hydrogen content of the weld will be reduced. So, for that also you will have to have there are many ways in that case for reducing these hydrogen content of the weld. It may be related to either the selection of proper electrode by heating the electrode, or taking care of the aspects related to the coating of the electrode or so. So, that way you have to reduce these, you have to have the control on the hydrogen content of the weld, because hydrogen is very much responsible for these lamellar tearing, because that hydrogen is leading to the embrittlement and in those cases your lamellar tearing may occur. Then you can also have the improvement in the design of the joint. So, by improving the design of the joint, you can ensure that there will be less chances of having these type of defects like lamellar tearing. So, for example, if you try to have the designs, so what you see that if you have you may have designs like here, and if you have a fillet weld. So, you have the fillet weld, if suppose it is going like this. So, in these cases you have the chances of the tearing, which is and on these places you may have the chance of the lamellar tearing, and if you if you go for the proper somewhat better design, so you can go for some fixing. So, that way if you do like this, so in those cases your designs are improved. So, this way the chances of the lamellar tearing will be. So, this is a poor design and this is a better design. So, you can change the joint design and that will lead to your the decreased chances of having the lamellar tearing. So, next we are going to have the discussion about so that is what we have discussed, that you have the these points we have already discussed, that what are the reasons for which these are promoted, and then next type of the cracking, which is very much important again, is the stress corrosion cracking. Now, what is happening that many a times when you have the welding going on, so you have the alloying ingredients are there from the which are coming from the electrode coverings and also fluxes. So coming among these these alloying elements which are coming from these electrode coverings or fluxes, they are very common. So, commonly they come into the weld pool. Now, what happens that they dissolve in the weld pool, but due to fast cooling, what is happening, because the cooling in welding is fast because of many reasons. That is what we have studied so far, because of the presence of weld metal, I mean metal on both the sides having higher thermal conductivity. So, you are getting lesser time to properly diffuse or mix or proper distribution. So, what is happening, that you will have the localized region where you have the high then chance high alloying elements, more highly alloyed regions will be there. So, there will be few regions which will have these alloying ingredients in a larger quantity than that is found in the bulk weld. Now, what is happening, that often when you have the formation of these regions, often these regions are the martensitic structures. So, and that will be giving you the problem in service. So, in future that leads to the problem in the service, and that is also because of these stress corrosion cracking. So, what happens, that you have the formation of these hot spots which are formed, and and these hot spots which are formed, they are normally encountered in case of SAW of so we have in those SAW processes, we are when there is a use of manganese. So, mostly in those cases these what happens, that some of the molten slags, they enter into the weld pool, and then it starts solidifying. So, that way this is also found many a times in the case of shielded metal arc welding also, and also the cord wires. So, these hard spots which are formed, they quickly solidify, and there is not complete dissolution. So, they require I mean since there is no complete dissolution. So, there is no complete dissolution, as well as there is not proper homogenization. So, all these, both these things are basically lacked, and that basically results into the stress corrosion cracking. So, if you talk about these mechanism of the stress corrosion cracking for the carbon steel welds. So, if you see, when these carbon steel welds are exposed to the severely corrosive conditions like warm or seawater. So, in those cases so there will be attack to be that will be concentrated upon the HAZ or the weld metal. So, that attack, so basically that limits the life of that weld. So, the effect of this this stress corrosion cracking is that once that attacks then that will be limiting the life of the HAZ. So, now again that depends upon the what kind of stress relieving treatment has been given. So, the stress corrosion cracking of HAZ basically will occur if the welded joint which has not been given the stress relieving treatment, and they are basically exposed to these aqueous solutions of hot concentrated these caustic soda, and in that case the weldment is subjected to very high level of stress. So, when these carbon steel welded joints are exposed to severely corrosive conditions, then there will be a tendency of attack on the weld metal or HAZ, and life of weld metal may be reduced. Now, what is happening that, so that is what we have studied, that stress and corrosion cracking of HAZ of weld occurs if the welded joint have not been stress relieved and are exposed to the aqueous solution of hot concentrated caustic soda, and so that way and the weldment is stressed in tension to a very high level. So, one is that in that atmosphere it is exposed, and then also it is under that tensile environment to a very high level. So, if you talk about the carbon steels, they are typically these type of cracks which you observe, they are normally intergranular, and if you look into the austenitic steels, they are normally found as the transgranular type of cracks. So, for the these carbon steels, more importantly, if you talk about the stress cracking reagents, stress cracking agents. So, they are the caustic soda, that is NaOH, and ammonium nitrate. So, these two are the stress cracking agents, and apart from that we also it has also been seen that these coal gas liquors, or you have cyanides and sulfates, they also act as the stress cracking tendency raisers. So, they increase these tendency to go for stress corrosion cracking. So, basically for that there will be a graph. So, as we see that for carbon steel you have the caustic soda and ammonium nitrate, they are the important stress cracking agent, and there is a limit of concentration and temperature value above which the stress relief of joint is required. So, basically what is happening that if you talk about the environment in which the material is to be subjected to, and so for that depending upon that concentration of the caustic soda and the temperature at which it is to be worked, based on that you can ascertain whether you require to give these this treatment or not. So, if it is falling in that case in a danger zone, then you have to give the stress relief treatment. So, basically that can be represented by a graph normally. So, you will have the temperature on the ordinate, and you have these this is the caustic soda concentration. So, the caustic soda concentration will be percentage by weight, and so it will be 10, 20, 30, 40, like that it will move. Now, if your caustic soda percentage is less, so it can even go to a higher level. So, and normally the graph goes like this, and this will be your 100. So, you have 80, then you have 60, 40, 20, and so. So, as you see that if your caustic soda concentration is increasing, then after this, so after this temperature you need to give the stress relief treatment to the material. So, in this case, if it is falling in the below zone, here the stress relief is not required, and here if you are if the material is going to be utilized or going to be used in that environment, corrosive environment, in those cases you will have to, and suppose the temperature is 80 degree centigrade, this is in temperature in degree C. So, if 80 degree centigrade is there, this caustic soda concentration should not reach maybe close to more than 16 or 17. So, that way according to this graph. So, if that is more, then you have to give these stress relief treatment. So, you have to give a kind of treatment in which what you do is you are going for heating, you are heating and holding that in between the temperature of 600 to 650 degrees centigrade. So, you are heating to this temperature, then you are holding for a specified time. So, holding for 1 hour per 25 mm of thickness. So, minimum of 30 minutes you have to keep for whatever thickness it be, be it even less. So, minimum of 30 minutes you have to keep, and then you have to do the cooling. So, cooling at a rate not more than 300 degrees C per hour. So, this kind of treatment you have to provide, then the material will not be subjected to stress corrosion cracking, even if it is used in the corrosive environment. So, this is in that toe area that stress corrosion cracking will be looking like, and in these in this under the corrosive environment, how the cracking takes place, that can be seen from this figure. So, these are the example of the stress corrosion cracking which is basically observed. Now, in the case of the austenitic stainless steels, if you look at the stress corrosion cracking of the austenitic stainless steels. So, in austenitic stainless steels, you have for these materials you have the low thermal conductivity and you have the high thermal expansion coefficient. So, you have low K and high thermal expansion coefficient. So, so what is happening that when they are limiting, they are subjected to the chloride containing corrosive media. In that case, these stress corrosion cracking may occur. So, that is what we have also seen, that when we are doing these welding of austenitic stainless steels, you have severe residual stresses are basically caused, and that is because of the property of these type of stainless steels, that is austenitic stainless steel. So, they have the low thermal conductivity and high thermal expansion coefficient. So, they will be they will have more contraction or expansion. So, in those cases when you are subjecting them to these chloride containing corrosive environment, in those cases you will have the appearance of the stress corrosion cracking. And if you look at these crackings, they are normally transgranular type of cracking, and also the branching is also seen. So, what you do is that when you provide in those cases, when you provide these heat treatment, so this stress relief heat treatment is carried out. So, there will be precipitation of the chromium carbide that will be taking place, because in the case of these austenitic stainless steels you will have so because of the chromium, so you will have the precipitation of the chromium carbide that will be so, but that is to be carefully seen. So, and also although these stress relief can be also obtained using these solutionizing also, so that you can dissolve these chromium carbide, which is about at the temperature level of about 1000 degrees centigrade. So, in that case there may be new residual stresses also that can be developed during that subsequent quenching. Now, so what is what we have seen, that you will have to have the proper treatment that is to be meted out to these materials, so that if you feel that this material is going to have the stress corrosion susceptibility, in that case you have to give the proper type of heat treatment, that is post weld heat stress relief treatment, so that you have the lesser chances of having these stress corrosion cracks in the materials. And also if you use these low carbon or stabilized grades of materials, then they can avoid the formation of these stress corrosion cracking, because they will allow the material to cool slowly after the solutionizing. So in those cases you can ensure that the undesirable effect in terms of these stress corrosion cracking can be avoided by having such grade of materials. So in a nutshell, we talked about these different types of cracks which we have studied, like in this class. In this lecture we talked about the lamellar tearing and the stress corrosion cracking. Apart from that, earlier we had studied about the reheat cracking or chevron cracking. So these are basically categorized as the special type of cracks which occur in different materials, and typically we have talked about the materials, that is steel. So and then you can have the also the analysis based on the other kind of materials like nickel based materials, or the materials which are used for specific applications like in nuclear. So these cracks and all that, they are more you have to have the more focus oriented studies on those critical components used in these nuclear industries or nuclear vessels or so. So accordingly when you are going to use them, or the material the component which is used to be used in the marine environment, so there you have to go for the special kind of treatment, so that they do not undergo these kind of crackings. Thank you very much.